Hi there, and welcome to the NBS Predictor tutorial. My name is Lindsay Fitzpatrick, and I'm one of the lead developers of this forecasting tool. In this tutorial, I'll walk you through what the tool does, how to navigate the GitHub repository, and how to use it to generate forecasts. Before we dive in, let's start with the basics. What exactly is Net Basin Supply, or NBS? Net Basin Supply is the amount of water being added to or removed from a lake basin over time. In this case, we're talking about each of the Great Lakes. NBS is driven by three key components: precipitation, evaporation, and runoff. Rather than forecasting water levels directly, scientists and forecasters often focus on NBS because it captures the physical processes responsible for water level changes. It really helps us understand, are the water levels rising because of above average precipitation or a decrease in evaporation? This forecasting tool takes in real-time atmospheric data from the climate forecast system, processes those inputs, and feeds them into state-of-the-art machine learning models trained on historical Great Lakes conditions. The result is a 12-month outlook for each of the Great Lakes. More specifically, the tool generates monthly forecasts for NBS, precipitation, evaporation, and runoff. The project was designed with a modular format, making it flexible and easy to contribute to. So whether you're here to run the forecasts, explore the code, or contribute to development, this tutorial will help you get started. So let's dive in. First, I'm going to assume that since you're here watching this tutorial, you probably already know where the GitHub page is, but I'll put it on the screen just in case. If you scroll down to the bottom, it should automatically take you to the README file. This README file is where you will find more details about the project, including in-depth overview, descriptions of the features, model inputs, the targets, and the data sources. There's also a data source table that lists the dataset abbreviations, their full names, and whether each one was used for training or forecasting. There's also links to their reference pages, just in case you want to dive into more details. Getting started. Before we begin, you'll need to have Conda installed along with Python 3.11 or above in order to run the forecasting scripts. To make setup as straightforward as possible, I've included step-by-step instructions in the documentation with all the required commands written out, so you can easily just copy and paste them as you follow along. For installation, I'll be demonstrating on a Mac, so I'm going to start by opening up a terminal window. The first step is going to be to clone the repository, which creates a local copy of the codebase on your machine. Before doing that, you'll want to decide where you'd like the repository to live. For this example, just for simplicity, I'm going to place it directly onto my desktop. Once you have chosen a location, we can clone the repository, and that downloads the project files locally. Depending on your internet connection, this could take up to a couple minutes. After the download is complete, navigate into the repository's root directory. This is also referred to as the project's top-level directory. Next, we're going to create a dedicated Conda environment for running the forecast tool. By using an isolated environment, it helps us ensure reproducibility and also keeps all the dependencies separate from your system-wide Python installation. To simplify setup, the repository includes an environment YAML file that defines all required packages and dependencies. We can use this file to automatically build the environment, which will install everything you need to run the tool. This step may also take a few minutes as Conda installs all the required packages and dependencies. Once the installation is complete, we'll activate the environment, and then we're going to set up a Jupyter kernel. Setting up the Jupyter kernel is a one-time setup step, so you won't need to repeat this in the future. Now, let's start by exploring the repository. To work with the Jupyter notebooks, we first need to launch Jupyter Lab. If you prefer not to use the notebooks, there are Python scripts available for all of the workflows that are included, so you can run everything directly from your terminal instead. After launching Jupyter Lab, it should open up a new browser window. On the left-hand side, you'll see the root directory of the repository. From there, we can navigate to the Notebooks directory. This is where you will find three main folders. The exploratory folder contains useful scripts that I used during research and experimentation. The validation folder contains scripts used for model evaluation and skill assessment. Finally, the production folder contains the operational forecasting workflow. The production notebooks are named in order that they should be run, hopefully making the workflow easy to follow. Step 0, or script 0, is the model training script. If you are an operational user, you are most likely provided with the pre-trained models and supporting files needed to run the forecasts, so you can actually skip this step. However, new users will need to generate these files from scratch. Fortunately, this process is relatively fast and painless and only needs to be done once. So we're going to navigate to the user input section of the notebook. In most cases, the only parameter you're going to need to modify is the local path. This is where you put the location of your cloned repository. Once that is set, you're ready to run the notebook. By going up here to this little fast forward button, you can actually click it and it will run all of the cells. If you prefer, you can click the play button and it'll run cell by cell individually. So now that that is run, we can double check and make sure that we have all the files necessary. If we go back to the root directory and click on Data and Input, you'll see climatology models and scalars. By going through these, you will find the pre-trained models saved. These were just created from that script, as well as scalars and climatology files. So it looks like everything is there that we need to continue on. So we'll go back to notebooks and production, and now we can go to script number 1. So step 1 is to download and pre-process the CFS forecast data. Again, we're going to scroll down to the user input section and change our local path. There's also a few other options here along the way, such as where do we want to download the CFS files? This can probably be left just as it is unless you want to put it somewhere else. Once the data is processed, it is saved into a database. This can also be moved, but you can probably just leave it where it is. There's also the source option. It's currently set to AWS, so the Amazon Web Services. This seems to be the fastest and is updated much more frequently than NCEI, but if you don't have the ability to use AWS, you can change that to NCEI. Here are some other options. Do you want to download CFS data? Yes. You might want to set this to no if you have to reprocess the data. Maybe your script crashed and you don't want to have to go through re-downloading it. Then you could turn that to no. Same thing with the process, just if something happens. Do you want to delete the files after they're processed? I currently have that set to no, just in case something were to happen. I don't want to have to re-download all of those files, so I'll manually delete them afterwards. There's also this auto option. It's currently set to yes. So auto will say if you are a operational user, you most likely have a database already set up locally and it is being updated pretty regularly. So being set to auto equals yes. The script will automatically go to that database, open it, find the last CFS run that was downloaded and processed, and it'll pick up from there. If you want to give it a specific time frame, that's completely possible. We'll just set this auto to no, and which is what I'm going to do for this tutorial. That way then I can just say, hey, will you please download just 1 day's worth of data? Now let's go ahead and run the script. So this is going to take a few minutes. It could possibly take up to an hour depending on how much data you are downloading and processing. If you're doing an entire month's worth of data, it could take 1+ hours. But because I'm only doing 1 day for this tutorial, it should only take a few minutes. We can scroll down here and watch the files download. Then it will process them, and once the script is complete, it will say, hey, we are done with this day, and then it'll start the next day. If it is downloading multiple days worth of data, then it'll say process complete, so you know that everything was downloaded successfully, processed, and saved to the database successfully. So now we can go to script number 2. This is the official NBS Predictor tool. So this is the script that is going to do the forecasting. So it's going to take all of that data that we just downloaded and input it into the pre-trained saved models and spit out the forecast. So again, we go to the user input section and change our local path. Everything else should basically stay the same, except that I did change the database to one that I currently have saved on my machine. This one already has archived CFS data on it. It has several months worth, just for the example, so you can see a full forecast. Once the input data is run through the trained models and a forecast is created, it will save the output into a new database. That way then you have the forecast separate from your inputs. So now we should be ready to run the script. This script really doesn't take that long to run, just because we've already done all of the hard work. We've already downloaded all of the data and processed it. So we're really just reading in that database and then running it through the model. There's some options along the way. If you want to possibly save the output data as a CSV, this is just a user preference. Maybe you're not very fluent in using databases. There's some also optional formatting of the output, and there are some examples here on what that formatting looks like. Again, this is just user preference. If you want the components to be different columns, and the forecast month that it's valid for. So here's just another example of the output. I know this one is preferred by the Army Corps, so it has the lakes and the components as columns, as well as the value in millimeters, and also calculates the value in cubic meters per second. If we continue to scroll down here, there's some other options of calculating mean values, saving them. That's all turned off at the moment. Calculating the climatology exceedance probability. So what this is it looks at the climatology and it determines what is the fraction of climatology that exceeds a given value at a certain location and a certain time. So this script will calculate those values and it'll save them to a CSV, and then we will read them in script 3. So step 3 is the forecast visualization output. If you're an operational user, you probably have your own scripts for creating plots, and that's completely fine, in which case you can skip step 3. That's why this one is separate, so that way then it's optional. So we're going to go down again to the user input, and we're going to change that local path. We're also going to make sure it is set to read in our forecast database, and then we're going to hit run. So it's going to create plot 1, which is a multi-plot figure. It has each of the components across the top as columns: precip, evap, runoff, and NBS. It also then has the lakes that it's valid for across as rows: Superior, Michigan, Huron, Erie, Ontario. The forecast that it's valid for is across the bottom, so there's our 12-month forecasts. And then the time series. the different colors represent the mean value for each of those machine learning models. So we have our Gaussian process, neural network, random forest, and XGBoost. We also have a 95% confidence band. So this is, because it's an ensemble forecast, it will automatically look at our 95% confidence band. If we have a wider band, that means there's a bigger spread between the forecasts and each of the models, whereas a much tighter band means that there's much more confidence or agreement between the forecasts and the models. Plot 2 is the exact same as the plot above, however, it saves it as an HTML and it's interactive. So if you want to get in there and see what are the different models, like here we can look at what forecast that's valid for, which model, the XGBoost, and exactly what the value is. So that kind of makes it a little more easier to view the different data sets. Plot 3 is just the NBS, so this focuses in on the NBS forecast, and we've added now climatology. So looking at these lines before, we couldn't tell if we were forecasting above or below average values. So now by adding the climatology lines, we can see, oh, look, Ontario and Erie, those forecast lines are above climatology. So we're probably expecting some wetter or more wet conditions than average. Plot number 4 is where we go back to that climatology exceedance probability, or CEP. This is also known as the probability of exceedance by the Army Corps, and it's just the fraction of historical climatological values that exceed a given forecast value for a specific variable, location, and time period. So these values range from 0 to 1. If you have a value close to 0.5, that means the forecast is near climatology or normal conditions. If you have a value above that, let's say 0.9, that says that 90% of our climatology exceeds our forecast, or they are above the forecast. So most likely our forecast is drier than normal conditions. Low values, or like let's say 0.1, would represent that 10% of climatology exceeds that value, which most likely means that we have wetter than normal conditions. So this is just a time series that it plots those forecasts, those CEP values, based on the month that they are forecasted for. Again, the different colors represent the different machine learning models over time. But figure 5 is probably my favorite. So this is a spatial map of the CEP values. It is a multi-plot figure, each box representing a different month that the forecast is valid for. So this particular one is just looking at random forest. They are lake-wide means. And intuitively, we can look down at the color bar and you can see that those orange and browns represent drier than normal conditions, where the darker the brown, the more like drier than normal conditions you would expect, where these blue and greens are wetter than normal conditions. So you can kind of look and see how they evolve over time. You can also look at the difference between the different lakes. Some seeing wetter than normal conditions, maybe looking at this in the winter or the late fall into the winter, especially downstream into like Lake Erie, Lake Ontario. So all the steps that I just covered in this tutorial are also available in a detailed step-by-step documentation in the README file for future reference. There is also a project structure detailing where functions are hiding, as well as other resources that you might find helpful. There is also a section outlining how to contribute to the repository for anyone who might be interested in getting involved. Best of luck, and I really hope you found this tutorial helpful. Thanks!